In this video, we're diving into LLaMA 4, Meta's latest release in the large language model series. LLaMA 4 introduces three models: Scout, Maverick, and Behemoth. Among these, Scout and Maverick are publicly available as open-weight models, while Behemoth is still under training. Scout is the smallest model, featuring 17 billion active parameters across 16 experts, with a total of 109 billion parameters. It uses a mixture of experts architecture, which we'll discuss in a moment. One standout feature of Scout is its 10 million token context length, one of the longest supported by any large language model currently available. Maverick is a larger model, also with 17 billion active parameters, but it includes 128 experts, resulting in a total of 400 billion parameters. It supports a 1 million token context length. Finally, Behemoth, which is still in training, is the largest with a staggering 2 trillion parameters. Now let's discuss the architectural features of the LLaMA 4 models. These are the first LLaMA models to employ the mixture of experts MoE architecture. With MoE, each token activates only a fraction of the total parameters, making the model more computationally efficient for both training and inference. This efficiency translates into higher quality within the same training budget compared to traditional dense models. To understand this, let's compare the architectures. A traditional large language model, like LLaMA 3, consists of transformer blocks with an attention module followed by a feed-forward network. This feed-forward network involves large matrix multiplications, which are computationally intensive. In LLaMA 4, the feed-forward network is replaced with a mixture of experts layer. Instead of one large feed-forward network, we have multiple smaller expert networks. A router selects a subset of these experts to process each token, significantly reducing the number of active parameters. There's also a shared expert that processes every token, and the outputs from the selected experts and the shared expert are combined to produce the final output. This selective activation of smaller expert networks, instead of using a single large feed-forward network, drastically cuts down on computation and memory bandwidth. This hybrid approach allows LLaMA 4 to achieve superior performance and efficiency compared to its predecessors. Another fascinating feature of the LLaMA 4 models is their use of interleaved attention. This isn't entirely new, but LLaMA 4 adopts it to handle extremely long contexts, up to around 10 million tokens. Instead of stacking traditional full self-attention transformer blocks, LLaMA 4 interleaves full self-attention blocks with sliding window self-attention blocks. In the diagram, you can see this pattern. 3 sliding window self-attention blocks followed by a full self-attention block, and this pattern is repeated throughout the model. Sliding window self-attention focuses only on a subset of recent tokens rather than the entire context. This dramatically reduces the amount of key-value cache required for inference, enabling support for such long contexts. This approach, similar to what's seen in Cohere's recent models, is crucial for handling extremely long sequences efficiently. Another important innovation in LLaMA 4 is its use of floating-point 8 precision during training. By training the largest model, Behemoth, with FP8 across 32,000 GPUs, Meta was able to dramatically reduce training costs while maintaining high model performance. This training run achieved about 398 teraflops per GPU and used over 30 trillion tokens, more than double that of LLaMA 3. This move toward FP8 isn't just about saving resources, it's a reflection of where the industry is heading. Lower precision formats like FP8 are now a practical standard for training large models because they strike the right balance between efficiency and accuracy. Let's talk about individual models in detail. Starting with LLaMA 4 Maverick, this is a general-purpose large language model featuring 17 billion active parameters and 128 experts, totaling around 400 billion parameters. This configuration delivers high quality at a lower cost compared to the LLaMA 3.370B model. As you can see in the performance results, LLaMA 4 Maverick stands out as a best-in-class multimodal model. It outperforms comparable models like GPT-4o and Gemini 2.0 in tasks such as coding, reasoning, multilingual understanding, long context handling, and image benchmarks. It's also competitive with the much larger DeepSeek v3.1, particularly in coding and reasoning tasks. Now let's turn to LLaMA 4 Scout, the most compact model in the lineup, with 109 billion total parameters. Despite being the smallest among the three, Scout delivers state-of-the-art performance for its class. One of its most impressive capabilities is the dramatically extended context length. While LLaMA 3 supported up to 128K tokens, Scout pushes that boundary to an industry-leading 10 million tokens. This unlocks powerful new use cases like multi-document summarization, long context retrieval, and complex reasoning across extended inputs. To better understand how Scout and Maverick perform in long context scenarios, let's take a look at the Needle-in-a-Haystack (NIH) benchmark. This test evaluates a model's ability to recall a specific token, or needle, buried somewhere within a very long context, or haystack. The diagram here summarizes the results across three test settings. Left panel. This shows the performance of LLaMA 4 Maverick on text contexts up to 1 million tokens. Middle panel. This shows LLaMA 4 Scout handling text contexts up to 10 million tokens. Right panel. This illustrates a LLaMA 4 Scout on video contexts up to 20 hours, which is about 10.4 million tokens. On the x-axis, we have the context length, how large the haystack is. For text, it ranges from 1,000 tokens to 10 million tokens. For video, it ranges from 2 to 20 hours of content. On the y-axis, we have the depth percentage, indicating where the needle is placed within the context. 0% means the needle is at the start, and 100% means it's at the end. The blue squares represent successful retrievals, where the model found the needle. White squares represent failures, where the model couldn't retrieve the needle. Looking at the results, LLaMA 4 Maverick, left panel, performs almost flawlessly for contexts up to 1 million tokens, with just a few failures at deeper depths. LLaMA 4 Scout, middle panel, achieves perfect retrieval even with extremely long contexts up to 10 million tokens. For video contexts, right panel, LLaMA 4 Scout also performs impressively, with only a couple of failures at longer durations and deeper depths. This diagram highlights the LLaMA 4 model's capability to handle very long contexts and retrieve specific information accurately, making them highly effective for tasks requiring extensive memory and recall. Lastly, we have LLaMA 4 Behemoth, the largest and most powerful model in the LLaMA 4 family. It's a multimodal mixture of experts model with 288 active parameters, 16 experts, and nearly 2 trillion total parameters. Behemoth achieves state-of-the-art results in non-reasoning tasks such as math, multilingual understanding, and image benchmarks. Beyond performance, Behemoth plays a crucial role as the teacher model for the LLaMA 4 family. Meta used it to distill knowledge into Maverick, leading to significant quality improvements. This was made possible by a novel distillation loss function that dynamically balances soft and hard targets during training, enabling more efficient supervision and reducing training costs. And that wraps up our deep dive into the LLaMA 4 family. In short, LLaMA 4 marks a new chapter in efficient, scalable, and multimodal AI, supporting an impressive 10 million context window. Thanks for watching, and see you next time.